Hello friends, myself Professor a.k.chaubey, now present again today to discuss some other topics under the heading of Physics Made Simplest. Well, yesterday we were talking about the nuclear reactions and the conservation laws, etc., and some other about compound nucleus, or say something about direct reaction, etc. Well, we have some types of reactions also. So let me say a few words about the types of nuclear reactions. Means so what the types of nuclear reaction meaning is that nuclear reactions, you see, we have one very simple nuclear reaction, that is the elastic scattering. So what the elastic scattering is? I want to say a few words only to make the physics more clear to you. What the meaning of elastic scattering? Elastic scattering means when we say generally that the reactions where there is no energy loss, whatever energy of projectile, it remains same after nuclear reaction. But it is not 100% correct from the physics point of view. To understand the real meaning of elastic thing is that elastic scattering reactions are those reactions where the incoming particle is scattered in the initial channel. That means what was the initial channel? It means what was the momentum, what was the energy of the particle, what energy, momentum, and which particle coming. After scattering, it goes into same channel, means same quantum mechanical states. Its quantum mechanical state remains same. There is some energy loss, but that is not appreciable energy loss. Means there is energy loss for the conservation of linear momentum. Means recoil. The system recoils, so whatever there in the recoil momentum, so whatever energy loss for the recoil, and that is not appreciable. So it is said that in the elastic scattering there is no energy loss, or you can say no appreciable energy loss. Energy loss is there, but not very much, very small, almost negligible. And there is no excitation. Means the target nucleus, we have say projectile say X, and we have target nucleus X. Means after this, target nucleus, it is going in the same channel, means it remains same quantum mechanical state, and this remains also in the ground state, means no excitation. If there is excitation, means energy loss will be there, and this will go to higher excited states. So this type of reaction is elastic scattering, where the projectile remains in the same quantum mechanical state. There is no appreciable energy loss. There is no excitation of target nucleus. Target nucleus remains in the initial state, ground state. If there is excitation, means there is some energy loss. And then after de-excitation, some gamma ray will come. So that is not. That will be in the inelastic scattering. Inelastic scattering means where the projectile X interacts with the target nucleus capital X, and we get here X star, and this say X prime, means lower energy. and this goes into excited state. Excitation now. So excitation. Means target nucleus goes to higher state and projectile gets lesser energy. X dash, you can say lower energy. X is now in the slightly lower energy state. Some energy loss is there. And this goes to excited state. So inelastic scattering is that scattering in which X star goes to higher state and X star emits H nu. X star comes to the X ground state and emission of H nu, that is the energy, the excitation, gamma ray emitted. So in elastic scattering, we have gamma ray, the projectile goes with the lesser energy and target nucleus comes to gamma state by emission of a gamma ray. Well, in elastic scattering also you can say one another interaction that is not scattering but that is radiative capture. What the meaning of radiative capture? Means projectile is captured by target nucleus. And it is radiative means after capture only gamma ray is emitted, radiation is emitted, radiative capture. A capture where radiation means gamma radiation is coming out. So that means projectile X plus X, X is captured by X and we get here C. The C is X plus X. And this, after this, we get only gamma ray, means X, this remains same, X remains same. And after capture, this decays, C decays by emission of gamma ray. So that is the radiative, means it is captured, X is captured in target nucleus and it is only that it was here that X was emitted, that was inelastic scattering, where after energy loss we get gamma ray but particle projectile is also going out with the low energy. Here the projectile is not coming out, projectile is captured by target nucleus. We get compound system and then compound system decays by emission of gamma ray. It goes to the target nucleus, X. Well, you can call it not X, maybe some X dash you can say, or you can say Y. Because when X is absorbed by capital X, it becomes a new system. It will not be X. Sorry. So it should be changed, X changed to Y. And then gamma ray coming out. Means this is captured by this. We get a new system after capture. But this capture is radiative capture. Means only radiation, photon, that is the H nu gamma ray is coming out. And we have other captures also, that is called disintegration. Disintegration is the reaction where X plus X we get C, compound system, and this C disintegrates. Means we get here Y. Here the C disintegrates into Y1 plus Y1 or Y2 plus Y2 small or Y3 plus small y3 and so on. Means compound system formed by capture of projectile into target nucleus, this compound system disintegrates in several ways depending upon the energy of excitation. Means what is the energy of excitation? This is excited. So what the energy of excitation? So this depends. Residual system, Y1 is the emitted particle. This can be a proton, this can be a neutron, this can be any particle, combination of alpha particle or any other particle. But emission of this depends upon the energy of excitation. Higher energy of excitation, possibility of emission of two particles here. It can be Y1 plus Y1 dash and so on. Means two particles can also come out. Three particles can also come out. But it depends upon the energy of excitation of compound nucleus. Higher energy means we have say this is excited here. It is here, compound nucleus. Or it may be here, or it may be here. So depending upon, this may give this C or this C, this may give some other. So this may give many particles. This may give, say, maybe many particles, maybe two particles only, or maybe only one. Or also it is lower excitation, it may give only gamma ray. So this compound nucleus which is excited, this can de-excite depending upon the energy of excitation. This is excited by here, by the projectile X. X is giving. So it means it depends upon the energy of X. Energy of X is high, we will get higher excitation. Energy of X is low, we will get lower excitation. So excitation energy depends upon the projectile kinetic energy. That means this can decay by many particles, say proton, neutron, or combination of two neutron, one proton, etc. Or this may give decay by emission of two particles, only one proton, one neutron, or alpha particle, one particle, only alpha particle, or only gamma ray. Because energy of excitation is very low, only gamma ray can come. So this is the one particular radiative capture is one particular case of disintegration where no particle is emitted, only gamma ray. This disintegration means excitation where many particles can come out after the decay of compound nucleus. So this is the one interaction, one type of reaction. The other, you can say, another type of reaction is called, which is taking place at the higher energy. Higher energy means the projectile may be, say, few hundreds or few tens of MeV energy. So that is a stripping and pick-up reactions. So what is stripping and pick-up reaction? Well, stripping means you are taking something from projectile. Stripped. Projectile is stripped off, means something is taken. Projectile, something is taken from projectile. So that is the stripping means projectile, something is taken. Just like we have say projectile, say deuteron, and we have any target X. This deuteron is going towards target. This target takes either a proton or a neutron. It is possible that this absorbs, this becomes Y and this becomes a proton, or this becomes a Z and this is a neutron. It is possible that deuteron is made of a proton and a neutron. So one particle, neutron is absorbed here and it becomes Y and proton is emitted. Here in this reaction, proton is absorbed and neutron is emitted. So this is from deuteron, a two-particle system, we are taking something. So this is stripped off, something is taken, means neutron is taken, proton is emitted. Here proton is taken and neutron is emitted. So this type of reactions are direct reactions and maybe at high energy. Means here it is just type of surface nucleus reaction that projectile comes, just passes and interact with the surface of the target nucleus and takes a nucleon or gives a nucleon to the system. So these are mostly high energy reactions where projectile is stripped off. Or we can have, say, a proton plus X. It is possible that here we get Y, and this proton takes something, means neutron from here, and it goes at the neutron. Means from X a neutron is absorbed and proton becomes a neutron, and this becomes a new system. So this is, proton has picked up a neutron. Neutron is picked from nucleus. Neutron is taken, or it is possible that neutron is the interaction taking place, and here it becomes a Y plus neutron. Here neutron takes a proton. A proton is picked. Proton is picked, and neutron goes to the target nucleus, it takes. Means that it was the target nucleus, and you see neutron, this particle coming here, this takes, and this goes here as neutron. Neutron coming, it takes from here, a proton is taken and it becomes neutron. So picked. Something is picked up from the nucleus. Or stripping means here it was nucleus and neutron was coming here. Neutron was coming here, and this takes, say, neutron and proton is emitted. So picked. Something is taken, picked. It is stripped. It's stripped off, it is picking. So these types of reactions are direct reactions and high energy reactions, stripping and pick up. Now I will talk one another type of interaction which has got the application, importance of application, and that reaction, interaction, I will call, it is separate actually, a separate branch of research also, and that I will say that particularly important interaction where a nuclear fission. Nuclear fission means an interaction where a heavy system is a fission, means it is broken into lighter system. Just I give an example. That's a neutron is interacting 0 charge, 1 unit mass. Neutron is interacting, say, with the uranium 92, uranium 238. This neutron is interacting with uranium 238. That this absorbs, and it becomes, after interaction, it becomes 92 and uranium 236 because charge remains same, mass 239. And also the reaction takes place with the 235 also. And the reaction with the neutron with the uranium 235 also, that is 0 neutron plus 92 uranium 235 also. There it becomes 92 uranium 236. So this interaction, because this is very small amount in nature, this is the 99 point, you can say, percent. It is less than 1% in nature. So that this reaction gives X plus Y. After this gives X plus Y plus neutrons plus radioactivity, radiations that is alpha, beta, gamma plus Q, energy. So this interaction, that uranium absorbs a neutron and it becomes excited state, and then it is broken into fragments, X plus Y. Two fragments, medium weight. Higher weight uranium is broken into two medium weight nuclei and neutrons. Neutrons means it may be 2, 3 neutrons. Means more than one neutron. One neutron is absorbed and we get here after this more 2 or 3 neutrons here. So different combinations of medium weight nuclei plus more neutrons, and radiation means radioactivity plus energy. This number of neutrons is more than the initial. So it is called the chain reaction. Chain reaction means because we get more neutrons, these more neutrons further interact with the uranium to give more fission and more neutrons in number. More neutron means 2, 3 neutrons each time. So more neutrons coming out means a chain is produced, and that chain multiplies, so more energy is produced and more neutrons are produced. This energy, Q, is calculated from the mass difference of the initial and final systems. It is found that this Q is of the order of about 200 MeV. Means if one fission is there, after one fission, what we get? In one fission of uranium atom, one fission, we get about 200 MeV energy. This 200 MeV energy is associated with X and Y, means as the kinetic energy of fission fragments. Kinetic energy of fission fragments plus energy of radiations and this kinetic energy moving these, they produce heat. So this, in one fission, about, we can calculate by mass difference, about 200 MeV energy is released, and this energy is huge energy. This is fragments moving with the kinetic energy, and they are interacting with the system, with the surrounding, producing heat, and this radiations, alpha, beta, gamma ray, also radioactivity. So each fission is producing lot of radioactivity, lot of energy, heat. This heat and this chain reaction is producing more heat, more kinetic energy of fragments, then they interacting with the system. So more heat, more energy. This fission is, say, uncontrolled. So uncontrolled means huge energy and not in our control. This will produce unlimited energy. You can control, then this will be, if controlled, this will be useful. Means this will be useful for what? Reactor. And reactor will produce, it will be power reactor, it will produce electricity, it may be research reactor for the research purpose, it may be breeding reactor to breed the fission elements, fissile elements. So this reactor is having multi-purpose, that it can produce more fissionable material, it can produce power, electricity. So controlled energy fission is reactor. Uncontrolled if the fission is uncontrolled, well, uncontrolled fission means nuclear or atomic bomb, you can say. Uncontrolled fission is atom bomb. Controlled fission is the reactor. The reactor can be power reactor, reactor can be research reactor, reactor can be breeding reactor. So any type of. So this is the peaceful purpose of the nuclear energy. That is the use for constructing useful reactor, for power reactor or research reactors. And uncontrolled, where you can't control the reaction. If you can stop the fission, that is done by using the control rod. Control cadmium rods are there which absorbs the neutron, and fission reactor power comes down and it stops also. So using control rod, you can control the reactor working. You can stop the reactor, you can increase the working also. So controlled reactor is useful. Uncontrolled fission is atom bomb, and you know that is disaster. So you can use either controlled fission for good purpose, or you can use uncontrolled fission for the disaster. So this is useful purpose of fission and useful purpose of about, I told you 210 you can say MeV energy released per fission of the uranium atom. Okay? Now we can have some say problem like calculate the total energy released. Calculate the total energy released if 1 kilogram of uranium-235 undergoes fission. And taking the disintegration energy per event, taking say Q, energy released as about 208 MeV. I told 200 nearly, so this is 200 MeV. So now we can say we have to find out how many nuclei are there in 1 kilogram of the uranium-235. When we can find out number n, number of nucleus, or atoms you can say, atom or nucleus, whatever. Let us see first, calculate atom. How many atoms are present in 1 kilogram? And then fission will take place. In atom, Then we have how many nuclei means multiplied by the, we can get directly using Avogadro number, the number of nuclei. In 1 kilogram of uranium-235. So that we get N. N is equal to, using Avogadro number, 6.02 into 10 to the power 23, and this is nuclei per mole, and this is divided by 235, its atomic weight, and then this is per gram, so you have kilogram, so 1.0 into 10 to the power 3, this becomes gram. So you calculate this, then N becomes equal to 2.56 into 10 to the power 24 nuclei. Energy becomes now total energy released by all nuclei fission. This becomes simply multiply by 208 energy per fission into 2.56 into 10 to the power 24. So this will be the energy, and that will be about, multiply this, so this will be about 5.32 into 10 to the power 26 MeV. You can see 1 kilogram of uranium is giving you, after whole amount is fission, this much energy in MeV. You can convert this energy into 1 MeV is equal to 4.45 into 10 to the power minus 20 kilowatt hour, and that is 1 MeV equal to this much, and we have this much. So you can convert this into how many? That 1 MeV is this much, so you can convert this into kilowatt hour. So this will be equal to 23.7, this energy will be 23.7 into 10 to the power 7 kilowatt hour. This energy will be converted by this into kilowatt hour. So you can say that if 1 kilogram of uranium is fission, we are getting 23.7 10 to the power 7 kilowatt hour. Huge amount of power. 1 kilogram of uranium after fission is giving a huge amount of power. That is why the power generated by nuclear reactors is a tremendous amount of power, much higher than the power produced by the thermal power station or by the hydroelectric. So that is why the nuclear reactors are very important for production of electricity. Okay. Any other problem can be, we can do something, some important, some reaction, some power. Say, one more problem I can do. On, say, disintegration on disintegration of one atom of uranium-235, the amount of energy released is 200 MeV. The power obtained in reactor, the power obtained in a reactor is, how much power is there? 1000 kilowatt. How many atoms are disintegrated per second? How many atoms are disintegrated in the reactor? That is, how many atoms? Because this much power is produced. One fission gives this much energy. So for this much power, how many atoms are disintegrated? Well, you can get, say P power is 1000 kilowatt. That is 1000 and 10 to the power 3 watt. That is 10 to the power 6 joules per second, because this 1000 10 to the power 3, so 10 to the power 6 is watt, means joules per second. And this means 10 to the power 6, here 10 to the power 6 divided by 1.6 into 10 to the power minus 19 energy, that is EB per second. This means 6.25 10 to the power 18 MeV per second. So much energy per second, you see, and you can find out now N, because per fission there is 200 MeV, so you can find out number of nuclei disintegrated. N will be equal to 6.25 into 10 to the power 18 divided by 200 MeV per fission. This will be equal to 3.125 into 10 to the power 16 per second. So many nuclei are disintegrating per second to give you 1000 kilowatt hour. So that you can see. Okay, gentlemen, we can stop today here. We will, when meet again, we will do something, some other topic. So thank you very much.